In this lecture, I'm going to talk about associative learning models, one in particular. This is an attempt to quantify how animals learn. And we're going to use words like associative strength. It's simply how strong does an animal associate a stimulus with another stimulus, or a stimulus with a response. What's the strength of that association? So let's think about Pavlov. Ring a bell, give a dog food, ring a bell, give the dog food. It's had a couple trials, so one might assume the associative strength between the bell and the food is a little weak, not really strong. But if you ring a bell and give a dog food a lot, hundreds of trials, one could say, oh, there's a really strong associative strength between the bell and the food. Now, some quantitative models have been developed. There have been several. I want to talk about one that was developed because some results like blocking and overshadowing seem to give some problems to strict Pavlovian theory. So these models help to not only test theories and to quantify results, which we're always trying to do in psychology, but also make predictions about other things we might see. So the model I want to talk about is really one of the most famous quantitative models in learning. It's called the Rescorla and Wagner model and the Rescorla and Wagner equation. So it's based on some assumptions that really depart from Pavlov. So it's really important that you know some of the differences between Rescorla and Wagner and Pavlov. The first is that it assumes kind of a higher cognitive process. Now with Pavlov, two stimuli active in the brain, they associate. The active in the brain, if they're in temporal contiguity, they associate. And that's really very parsimonious, very simple. But where Rescorla and Wagner says, no, there has to be some surprise in what happens. It's based on surprise. Let me give you an example. Go up to a dog, you ring a bell, and the animal's listening to the bell, looking around, and maybe it tilts its head, but it has no expectation that anything will follow. And then the animal gets food right after the bell. Well, that's surprising. Wow, I need to, that's really important. I'm a hungry animal, so I'm going to make some really strong associations there. But if you keep doing this, trial 7, trial 8, now you're starting to get a chance where you ring the bell and the animal says, I have some expectation. I'm not as surprised that I got food. And so on that trial, on that 7th trial or 20th trial or whatever, a little less learning happened, a little less strengthening of the association happened than on the first trial because there is a little less surprise. We're going to quantify what I mean by surprise here in a minute. The difference between expectations and outcomes determine learning. That's what I was just saying. At the beginning of training, there's a big difference between expectations. I don't really have any expectations. An outcome, oh, I got food or I got shocked or something. There's a really big difference there, and so there's lots of learning. However, if the animal's been trained a lot, then it kind of expects to get food, and it gets food, so there's not a lot of learning. Now, the associative strength can range in this Rescorla-Wagner model between -1 and 1. It can be a single number between those two. So a -1 means that the stimulus is completely inhibitory. I know when I hear that sound, there is no way I'm going to get the US, food or shock or whatever. All the way up to 1. 1 is the most. 1 is asymptotic, meaning when I hear the bell, I know I'm getting food. I know it. It's perfect association. Now, what's interesting about this model is it really departs from Pavlov. Pavlov said a stimulus can be both excitatory, have excitatory associative strength, and be inhibitory at the same time. It can be excitatory and inhibitory. An example is the end of extinction. So if I have a pigeon and I turn on a light and I drop food in the hopper and we're doing auto shaping, and the light and the food happen hundreds of trials. When the light comes on, the probability of the animal pecking the light is really strong. It has a really strong excitatory association. But then if I present the light and do not provide food, and I do that for many trials, that's extinction. And Pavlov said there's excitation from acquisition. Excitation meaning the bell. The key light is going to follow with food. And inhibition. The key light is not. And they compete for each other. Performance is a function of excitation and inhibition. What evidence did Pavlov have that these things occur together? Disinhibition, spontaneous recovery, rapid reacquisition. But Rescorla and Wagner model says no. At the end of extinction, there is no association. So if you ring a bell and give a dog food so much that the associative strength gets up to 1, oh, that's a really strong association. Well, then, if I ring the bell and don't give the animal food, it's going to go from 1 down to 0. And this is a kind of a problem for Rescorla and Wagner to explain things like spontaneous recovery and rapid reacquisition. But they've found kind of ways to do it. Some of the ways deal with generalization and discrimination. We're not going to get too in depth with that. But here's a major difference. Pavlov says a stimulus can be both excitatory and inhibitory at the same time. And Rescorla and Wagner says it can be excitatory, it can be inhibitory, it can be 0, but it can't be excitatory and inhibitory. Now, remember Pavlov said that stimuli in a compound, 2 stimuli together, gain associative strength independently. The animal learns independently. Ring a bell, turn on a light, and give the animal a shock. The light and the bell both become associated with shock, independently of each other. This got us into a little bit of problem explaining things like blocking. But the Rescorla-Wagner model says associative strength is not gained independently. Components of a compound stimulus, the bell and the light are the components, share available associative strength. Share. This is going to be really important, and it helps us to explain blocking and overshadowing. All of these things are going to be explained in future slides. Rescorla-Wagner can also be used, or variations of it, in experiments on choice. Does the animal choose A or choose B? Does it choose the green light or does it choose the red light in order to get food? And what Rescorla-Wagner says, the probability of choice, although they never really modeled this, is dependent on the relative associative strength. We're going to get into that idea in section 3 of this class. So associative strength increases on reinforced trials. The light and the food, the tone and the shock, that's a reinforced trial. Reinforcement in this case doesn't necessarily mean something really good. A shock is bad. I'm just saying there's a presence of the US after the CS. And the associative strength decreases on non-reinforced trials when the CS is presented but the US is not. It goes up and down. The asymptotic or peak associative strength, the highest level of associative strength, depends on the value of the reinforcement. For example, one might assume that the most that can be learned is going to be different when the shock is a half of milliamp versus 3 milliamps, which is a little bit painful. Or ring a bell and give the animal dry kind of dog kibble. Oh, okay, that's not so bad. Yum, I guess. Ring a bell and give them cheesy bacon liver snaps. Oh my gosh, those are so delicious. Greater value, and one might say that maybe the asymptotic level could be higher. When we discuss this, we're going to kind of veer away from that. We're just going to say, if we give a reinforcement, if the US is present, the most they can learn is 1. We're not going to vary that, though many people have. Well, there it is. There's Rescorla and Wagner's model. And we're going to go through it line by line, and then we're going to simplify it a little bit, and then we're going to do a little bit of math. So, the first thing is delta VA. So, V represents, in this model, the strength of association. The strength. V is the strength of association. If you have stimulus A, then one might say V sub A is the strength of association of A. A might be a tone, a bell, a light, whatever. But it's the strength that that stimulus is associated with the US. Delta is a Greek letter that's oftentimes used in chemistry. You see this in chemistry books. It just means change. That's all it does. It just means change. So this is representing a single experience, a single trial. What is being changed on that trial? Let me give you an example. Let's say stimulus A is a tone. Beep. And on that trial, the sound beep comes up, and the animal is given some lemon juice in the mouth. A little Pavlovian thing. Well, how much association changed to that tone on that trial? That's what this is asking. This is representing a single trial. Now, in Rescorla-Wagner model, the alpha here is a value that can change. It can change from 0 to 1, and it's the salience of the conditioned stimulus. What do I mean by salience? How bright is it? How loud is it? How much does it gather the animal's attention? An animal might have a difficult time learning if you play a tone that's really soft or the light is really dull or something. Again, we're going to modify this in just a bit. Beta is the speed of learning for the US. This is US related. And again, we won't deal with that in the modeling we're going to do. But this is, in some way, will tell us how fast the animal learns. These two variables here. Then we get to lambda. That's lambda right there. Lambda is the theoretical asymptote of learning. It's a reflection of the US. Simply stated, lambda is the most that can be learned on any given trial, the most possible that can be learned. And when people model this, they might change lambda depending on the quality of the US. How good is it? How strong is the shock? How delicious is the food? But let's make things easier. Let's just say the most that can be associated on any given trial is either going to be 0 or 1. This is what I mean. If I ring a bell and I give the dog food, I've done a trial where the CS is presented, the US is presented, the most association that can happen, the most possible that it can reach to is 1. On reinforced trial, lambda for this lecture is just going to be 1. If I reinforce it, we're just going to say lambda is 1. If I ring the bell and don't give the animal anything, well, the most it can learn is 0. There's nothing there. There's no food. Play a tone and no shock, there's lambda 0. So, for our modeling purposes, just for this, we're going to say lambda is 0 or 1. Lambda is 1 if the US is presented, 0 if it ain't. Okay? Simple as that. Then, this is simply representing all that has been learned. All the association, T stands for total. And if we're just doing one single stimulus, it's the associative strength of A. So let's think about this for a moment. If A is a tone and I haven't reinforced it at all, the association on that trial is probably zero. The animal's coming in. I've heard the tone. I've never seen that associated, never heard that associated with anything before. But as the animal learns, this value increases. That makes sense. The more the tone is presented with the food or the lemon juice or whatever, the more that happens, the stronger the association. So let's put this really simply. What is learned about a stimulus? Well, it depends on the difference between what can be learned and what is already known. That's all that is. It's the cumulative associative strength of all the stimuli the animal's dealing with. If it's just one, fine, it's just one. Just stimulus A. But sometimes we have stimulus A and B, and we got to take both of those into account. That's where we can start explaining overshadowing and blocking. What can be learned and what's already known. This right here in the parentheses can be understood as surprise. That's all. That's the quantitative surprise right there. If what's most can be learned is one, what the most can be learned is one, because I'm ringing a bell and I'm giving the dog food, and it's on the very first trial, that's zero. The difference between 1 and 0 is 1. That's a really powerful thing. But if the animal's learned something, then it's not as surprised. If the associative strength of a stimulus is 0.5, well, it's not 0, it's not 1. But how much that animal's going to learn on that trial is going to depend on that difference. We're going to do some examples here. Now, when I was at the University of Hawaii, I worked with two researchers, Pat Kuvion and Jeff Bitterman. And I did my PhD with them. Learned a great deal from them. And we used a variation of this model to not only account for honeybee learning, but also predict honeybee learning in other circumstances. So, here's a paper that I wrote a long time ago. There's me, there's Pat Kuvion, people called him Jeff Bitterman, but his first name was Mort, but everybody called him Jeff. And you can see we did some research with honeybees, and we used a variation of this model right there. So I'd like to talk about that because I think that model, which is very similar to the Rescorla Wagner model on its assumptions, is a little easier to understand, and I think still gets the point across. So here's the model. Again, it's very simple, similar to the Rescorla Wagner model. By the way, if you're ever wondering, these are called linear operating models. So in this case, on any given trial, what is the change in associative strength to A? It's alpha times lambda minus what is known, the total associative strength. Now, the only real difference here is we're not dealing with alpha and beta and the salience of this and the salience of that. We talked about alpha as just rate of learning. How fast does this animal learn? It might be very similar for a species. Like a honeybee might learn more slowly than a pigeon, and a pigeon might learn more slowly than a dog, or whatever, right? This is kept pretty constant. It doesn't change through the experiment, but we can model for it. We can simulate and see what fits best and what is the best learning parameter. Again, lambda is the theoretical asymptote. If the animal is reinforced, if CS and US are presented, it's 1. If the CS is presented without the US, it's 0. Simple as that. And of course, the associative strength of what they know. Coming into this trial, this single trial, what expectations does it have? So, we have this, what is the change in associative strength of A? And then we have an additional component to this model that the V total is the sum, it's the summation of the association of A and the association of B. These are just two stimuli in a compound. If you present a light and a tone, you have both of them have association. If they're both presented, we got to add them up. because the animal's looking at both of them and getting information from both of them. All right. So let's just look at some of the differences. First, we're not going to change this much, but you should know. If I was to model something with different lambda values, lambda value of 0.7, a lower one, maybe it's not as an intensive a shock. Maybe it's not as high of sugar content for honeybees. That's what I did. The most it can learn is 0.7, so the learning goes this way. Now, this is called an increasing decelerating function. And the animal learns a little less on each trial because as it has trials, this number increases. And so it has some expectations, and so it learns less on each trial. This is a lambda of 1, asymptote of 1. This is our assumption for this lecture. I just wanted to kind of show you the difference. These are different learning rates. Alpha values. Alpha values. The higher this value, the faster they're going to reach an asymptotic level. Now, we can assume that this is not 1, which means they learn everything on one single trial. And by the way, alpha has a range between 0 and 1 in our equations. 0 and 1. It can be 0.15, 0.25, or it can go really fast, 0.50. That's the range. And this is just how quickly, how many trials does it take to reach an asymptotic level. And you can see that as alpha is 0.5, and I simulate this. I made these on Excel. I did the Rescorla Wagner model variation in Excel. You can see it learns. Wow, it really is learning. And it finally reaches that asymptotic level way up here. It approaches 1. It approaches 1 at about 80 trials because the animal doesn't learn that fast. But look at this one that's 0.5. Boy, that animal really learns quickly. It reaches an asymptotic level, wow, only 20 trials. This is important in our mathematical modeling. Let's go ahead. I'm going to call this the Rescorla-Wagner model, even though Cuvion and Bitterman did a variation on it. I think it's just important. We'll just kind of assume this is the same kind of thing. They do have some differences, but for this lecture, let's just assume we're talking about the Rescorla-Wagner model. So here we are. We're going to do a single trial, and we're going to have stimulus A. Let's do a Pavlovian salivating dog. It's just fun. Stimulus A, we'll say, is a metronome. Beep, 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 beep. And when that sound comes on, it's a little metronome, how much does the animal learn? And we'll say that alpha, it has a learning rate of 0.25. This is arbitrary. I'm just using this number. We might model for it, but let's just use it to understand the equation. And lambda is 1. Remember, lambda is 1 if they're reinforced and lambda is 0 if they're not. Let's do an equation. What did the animal learn on that trial about the metronome? What is the change on trial 1 to the associative strength of stimulus A? Stimulus A, in our case, is a metronome. The animal is given some food, so lambda is 1. But what does the animal know coming in? Now, this could be V total, VT, but we're only dealing with one stimulus here, so we might as well just call it the associative strength of A. If we had many different stimuli, A and B, we might call that total. But this is simple. Trial 1, it's asking, what does the animal expect? Let's try 1. It's never heard the metronome in its life. It doesn't think the metronome is going to follow with food. It's not thinking anything. It has no associative strength on trial 1. That makes sense. It's trial 1. There's no learning. But what changes? What changes after the metronome is played and the animal gets food in its mouth? The change is equal to 0.25, that's a constant, times 1, it was reinforced, minus the associative strength coming in, which is 0. So the animal has changed 0.25. Let's do trial number 2. So it goes from 0 to 0.25. Let's go on to trial number 2. It's had some experience. What's the change in associative strength of A? Well, equals 0.25 times 1. Why is it 1? Because it's reinforced. Metronome plays, we get food in its mouth. But look at this. It has some expectation. Why is this 0.25 here and 0 here? Well, because it's 0 here because it's the first trial. The animal had no expectations at all. But after the first trial, the metronome sounded, it got food, maybe there's a little expectation there. And so the difference between these two numbers is less. So the animal learns less. 0.25 times 1 minus 0.25, which is 0.25 times 0.75 equals 1.875. You can see that the change is high on the first one and it's a little less on the second one. This can be represented this way, see? 0.25, this is the one in yellow, up, 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 okay? Each time, it's going to learn just a little bit less than it did on the trial before. Okay, so alpha remains the same. These represent trials. Trial 1, 2, 3, 4, 5, 6, 7. These are trials. The total has to be added. So on trial 1, it changed 0.25. On trial 2, it changed a little less because the total's here. Now I'm going to add the 0.875 to the total, and the total increases. And so a little less is learned because this is representing right here expectation. Expectation. What do I expect on that trial? You can see expectation goes way up. And so on each individual trial, it learns just a little less. And that's what's shown here. This Excel spreadsheet is shown here. So this is the change in associative strength on first trial way up high. And the total on the second trial, the total is 0.25 because that's what it learned on the first trial. But that made learning just a little bit less on that trial. Didn't learn as much. Why? Wasn't as surprised. Now the total, we're going to add this and this together, and we're way up here. Well, now the animal has some real expectations. I've heard that metronome 3 times, and 3 times I got food. So it's going to learn just a little bit less. There's less change. This is the cumulative score of association. This is, the blue is how much the animal associates the stimulus with reinforcement. It goes up and up and up. The red is how much it learns on that one trial. And because it expects more, it learns less. Why? Because expectations are met. Here we are on the 7th trial. Metronome plays, it gets food. I kind of thought I was going to get food. There isn't a big difference, and so I don't have as much learning. So let's look at how Rescorla and Wagner model would deal with overshadowing. This is the design of overshadowing. Group 1, A and B are reinforced together. Whatever this is, a blue light and a tone. And this is just a blue light. I think we're getting to the point where we can just say A is a stimulus, and plus represents reinforcement, and negative means non-reinforcement, or just at least a test. So let's do a trial. We say, what is in this trial when A and B are presented together in compound? What has changed to A? What has changed to A? Well, the change to A is 0.25 times 1. It was reinforced, minus 0, first trial, 0.25. And we can assume that the same thing happened to B. What is the change of B? It's 0.25 times 1 minus 0 is 0.25. What's the total? A is 0.25, but the total is 0.50. here we are with trial 1 with just A by itself. Remember, we're comparing these two groups. This is group 2. And after one trial, the associative strength of A are the same. And in fact, people predict you can't see overshadowing if we just do one trial. But let's do number 2, the second trial. What is the change? This is the second time A and B are presented and reinforced. What's the change of A on the second trial? Delta VA change is 0.25. Alpha is a constant here. 1 is got reinforced. That's lambda. That's lambda right there. It's just reinforced. Minus all that is known. That's the total. And we have to add A, 0.25, and B, 0.25 together, and we get 0.5. And so what's learned on the second trial is 0.125, just quantifying it. So now what's VA? It's 0.25, because that's what it learned on the first, plus what it learned on the second, 0.125. So on the second trial, the associative strength, which can range from 0 to 1, is now up to 0.375. But the total, we add them together. Let's look at this on the second trial by itself. 0.25 times 1 minus 0.25 is 0.1875. If you look, this is different because it's in a compound, both of them. And this is by itself. And so at the end of the second trial, the associative strength of A by itself is 0.4375. But this one's less. And that's the result of overshadowing. The overshadowing says components in a compound together, animal learns less about A than by itself. Now, we explained that before as the possible explanation of afferent neural interaction and generalization decrement, but this is just quantifying it using a Rescorla-Wagner model. Let's do the third trial. What's the change of A when A and B are reinforced together? It's 0.25 times 1 because they got reinforced, minus what is already known. And what is already known is the combination of A and B, 0.75. 1 minus 0.75 is 0.25, and what is learned is 0.0625. What's the total? Well, it knew this before. A before was 0.375. We're going to add them. Add what it learned on the third trial, cumulative, 0.438. This is the third trial when A is reinforced by itself, and you can see it not only learned more, but it has a higher value after 3 trials. What is the result of overshadowing? Animal doesn't respond as much to A here when conditioned and compound compared to when it's by itself. And the Rescorla-Wagner model predicts that quantitatively. So, the associative strength of A when reinforced A and B together is only going to get up to 0.5. That's the most because it shares available associative strength. A by itself, way up here. And so we can see that they start getting different after the second trial. And if I was to train for 15 trials according to this little pattern and say, what does the animal respond to more? A by itself or A that had been conditioned and compound? The associative strength is very different and the actual behavior is different. Associative strength of A can only get up to 0.5 because they share available associative strength, and here it can get all the way up to 1. So of course the animal is going to respond a lot less here than here. Now let's look at blocking. Blocking is when one stimulus is reinforced, then it is reinforced in compound with another stimulus, reinforce B, then A, B together, then test A. And the control group reinforces C and then gets rid of C and then just A, B, and test A. Let's look at blocking quantitatively. Let's say in the first stage we reinforce B so much, boy, that is really strong. B is followed with reinforcement trial after trial after trial until it reaches the highest possible asymptotic level that just rounds up to 1. It is a perfect predictor of reinforcement. If I then present A and B together, first of all, what do you think is, according to Rescorla and Wagner, what is happening here? The animal sees B and goes, oh, I'm going to get reinforced for sure. I guarantee it. I had all this training. I know for sure. So no learning is going to take place on that trial. Even though A is presented with reinforcement, the animal already predicts perfectly its environment. There is no surprise, so there's no learning. So let's say I reinforced stimulus B until the associative strength of B is the highest it can be. Then in stage 2, A and B together. You add them up, V total. A is 0. It's the first trial. It's the first trial here. It means nothing. But B is 1. 0 plus 1 is 1. So what is the change in associative strength to A? It equals 0.25 times lambda. Lambda is 1 because it's reinforced, minus what is already known. And B is telling them all they need to know. And so 1 minus 1 is 0. 0.25 times 0 is 0. Nothing's learned. Nothing's learned. And that explains what's happening. Because the animal has already learned that B is a perfect predictor of the outcome, it doesn't need to learn anything. Bring in another stimulus, it doesn't care. B is telling me all I need to know. I'm not surprised. I'm not going to learn. Let's practice a few other. Let's look at extinction and condition inhibition, and then we'll call it, okay? So here we are in extinction. First, we have acquisition. Okay, animals learning. Associative strength increases. We'll just say alpha is whatever it was, 0.25. And then on the 12th trial, the stimulus is presented, and there's no US. That's the definition of extinction. Acquisition, extinction. And there's a drop in associative strength. Let's look at that quantitatively. So at the end of acquisition, we'll say the V total, or VA, whatever, is equal to 0.9. Kind of looks like it's about there, and maybe a little higher, but let's just say, for making the math a little easier for us. At the end of acquisition, we're going to say VT, V total, the associative strength of A, whatever, is 0.9. If you look at it, it's maybe a little bit more than that, but let's just make the math a little easy for us and just say that's about 0.9. Then on the 12th trial, right here, it's not reinforced. That's extinction. So here's the equation. What's the change in associative strength of A, right here, when it's not reinforced? It's 0.25 times 0 minus 0.9. Why is it 0? Why is lambda 0? Lambda's been 1. Well, because lambda is 1 when it's reinforced and 0 when it's not. It's the most that can be learned. And when it's reinforced, it approaches and gets up to 1. When it's not reinforced, it decreases and gets down to 0. So lambda is 0. The total is 0.9 because we've already had some training. There is some expectation. On the 12th trial, when I present the stimulus A, the animal's going, oh boy, I'm getting reinforced for sure. Yes, what? Huh? What? I didn't? Well, that is surprising. 0.25 times a negative 0.9 is a negative 0.25. It's lost associative strength. It had 0.9. We subtracted 0.25 because that's what it learned on that trial. It lost associative strength, and now we're dropped down into 0.675. We're dropping down. We keep doing that. We keep dropping. Finally, let's look at condition inhibition. Here's condition inhibition. Here is the design. A plus, A, B minus, A plus, A, B minus. A is reinforced, but not when in the presence of B. And we know from this that B becomes inhibitory. It is a signal of non-reinforcement. Passes the retardation test, passes the summation test. And we're concerned about A in this experiment, but we're really concerned about B. What is happening to B? So let's look at what happens to A. What is the change in A on this trial? delta is the first trial. What is the change of A? It equals to 0.25 times 1 because it's reinforced, minus 0 because it has no expectations on the first trial. And so now it changed, gained 0.25. So what are the two together? After the first trial, A is 0.25, and after this trial, B is nothing. Why? Because the animal hasn't seen B yet. That's the next trial. The total is 0.25. Now, what happens when we then do the next trial, AB minus? What is the change to B? Change to B is equal to 0.25 alpha times 0. Why is it 0? Not reinforced. A and B are presented, and there is no food, there is no shock, there is nothing. But the animal had a little bit of expectation because A is telling them, oh, I might get something because I got something on last try. I might get something, a little bit of expectation. So what's the change in B? Because we take all that's involved. This is all the associative strength of A and B right here, the total, minus 0.0625. What is the associative strength after that trial? Negative. Negative. That means it's inhibitory. Remember, negative numbers means that the stimulus is a signal of non-reinforcement. Positive numbers means it's a signal of reinforcement. B becomes inhibitory. It's not reinforced when reinforcement is expected. So it loses associative strength. All right. I think this kind of lecture takes a little work, takes some practice, and certainly try out these models. It's not so bad once you work with it for just a bit.